So a good introduction to a mass spring damper system is to simply set up the mass spring damper system. So let's go ahead and set up a wall here. And along with our wall, let's set up a floor. Now, a rule about this floor, there's no friction on it. And these little lines are going to determine no friction. And so off of this wall, what we're going to have is two things. We're going to have a mass, we're going to represent it with a box, and we're going to have a spring, which we'll just draw like this. Now the box has a mass of m, so you don't have to think of it as a box, it's just a mass, and the spring has a spring constant of k, right? So how would we model the motion of this mass on a spring if we, say, push the mass that way and we were going to watch it over time? We would see that it would probably go back and forth, oscillate. So we know from mechanics that there is a way to quantify this relationship, and it comes from the formula, or rather Newton's second law, which states that the sum of all forces acting on an object is going to be proportional to the acceleration that object experiences. Specifically, the constant of proportionality is the mass of that object, again, times the acceleration. So what do we know about the forces acting on F? Well, there's only one force-acting object here, or rather force-inducing object on M here, and it's K. It's the restoring force coming from the spring. So what do we know from mechanics about the restoring force coming from a spring? Well, if I call this F of K for the spring force, it's going to be equal to negative the spring coefficient times the distance x, where x is the distance from equilibrium. So for example, if this is the length at equilibrium, let's call it E, then this distance over here, let's call it to the center, is going to be x. So the reason that it's negative is because the restoring force pulls backwards. So if the length of x is positive, the spring is stretched, then the restoring force is going to go backwards and compress it. And likewise, if it's compressed, it's going to go the opposite direction and expand. So we know this about our spring force. So we can also see that there are no other force-inducing objects, at least on the mass, so we can conclude that this is all the forces acting on the mass. So we can set up an equation minus kx is equal to, now instead of saying ma, we can recall that acceleration is simply the second derivative of position, and we can say mx double dot. Now this double dot notation is equivalent to the double prime notation, or if you're more familiar, dx squared dt squared, or rather, my apologies, d squared x dt squared, which are all the same way of saying the second derivative of x with respect to time. The key thing is about this notation, the dot notation, also known as Newton's notation, is that it specifies time. So if you use dot notation on any variable, that automatically means dt. However many dots is that however many derivatives. If you use prime, it's not necessarily time. It can be, but it doesn't have to be. With this form, we can rewrite our equation as mx double dot plus kx is equal to 0. Now this may be a form that you're more familiar with, and you may already know where to go from here, but instead of immediately going for adding a damper, let's take a look at this equation, see how A, we can simplify it, and B, how we would find a solution for it if we wanted to. Right? So the first thing I want to do is let's get rid of this factor of m out the front, because it's always nicer to have the coefficient of the highest order derivative be 1 if we can. So to do that, we're going to have x double dot plus the square root, no square root, I'm jumping the gun there, k over m, x equals 0. Now, for convenience sake, what I will do now is I will define a term, omega naught, is equal to the square root of k over m, I jump the gun, such that we rewrite this equation as x double dot plus omega naught squared, again, where it's just a constant, x equals 0. Now, the reason I do this comes from on high, and it's a bit of foresight, but if you're familiar with mechanics, you know that a spring and mass system has a resonant frequency. In other words, it has a frequency at which the oscillation back and forth will optimize the energy such that the amplitude of the oscillation is maximal. In other words, if you were to move the mass back and forth, or rather, if the mass were to be moving back and forth at this specific frequency, omega naught, called the characteristic frequency or the resonant frequency, then the amplitude of that resulting motion would be the maximal it could be out of any other frequency of oscillation. Well, this is a fact you could derive from physics, but it's also something we can derive numerically later with the method of undetermined coefficients or Laplace transforms. But in this case, we don't even have to go that far. When solving this equation, it turns out that if we make this nice substitution, it makes all the numbers nice and at least easier to look at later. So trust me on this one, but you'll see where it comes on or where you could work backwards from it. So now that we have this equation, we don't exactly know a method by which to solve it, but we can make an educated guess. Remember that if we disturb this system, it's probably going to oscillate back and forth. As well, if you know from your intuition, whenever you have something on a spring, because it's the real world, there's friction, there's this and there's that, it may also slow down and come to a stop, so it may decay. There's a bunch of functions in mathematics that we know for this kind of behavior, for example, sine and cosine, the exponential, the hyperbolic functions, cosine, and the exponential function, which also has decreasing behavior. Well, what if I told you all three of these functions were actually related? And in fact, they are. Well, it's obvious that e to the x is related to e to the x, but we do know from calculus or pre-calculus that the hyperbolic functions have an expression e to the x plus or minus defines whether it's cosine or sine hyperbolic, e to the minus x over 2, and this gives you the hyperbolic functions. And then likewise, if you'll remember from your previous courses, or if you've never seen it before, welcome to Euler's identity, e to the I theta, where theta is just the variable, is equal to cosine of theta plus I sine of theta. Now, a neat, interesting trick, if you've never seen this before, is if I ask you what is the value of e to the I pi, well, this may seem like nonsense. How do you multiply a number by itself an imaginary number of times, let alone pi times? But using the Euler identity over here, we can just say this is equal to cosine of pi plus I sine of pi. Well, we know I sine of pi is 0. And we know cosine of pi, we know sine of pi is 0, therefore I sine pi is 0. And we know cosine of pi is -1 on the unit circle, so we can just say e to the I pi is equal to -1. That's a fun side note for you right there about the Euler identity. So using that fact, we can make an educated guess that our solution is probably going to look like an exponential, but because we need to give it some wiggle room, let's give it a constant coefficient out over here to allow us some freedom when we're choosing our constants of solution. And in fact, for it to satisfy the equation, there has to be some constant manipulation for it to equal 0. So let's just plug it in and see what we get. Well, the second derivative of e to the RT is going to be r squared, e to the RT, plus, and we keep omega squared here, it's a constant, omega naught squared. And we don't take any derivatives for this, so we just get e to the RT. And this is still equal to 0. Well, now if we were to factor out e to the RT, what are we left with? We're left with r squared plus omega naught squared is equal to 0. Now, there's many direct arguments, algebraic arguments you can make, but the easiest one to show that this implies that r squared plus omega naught squared is equal to 0 is just to recognize the fact that there is no value r or t, or rt for that matter, that will make e to the rt equal to 0, just as there's no defined output for the natural log of 0. So we can safely divide both sides of the function by e to the rt, or rather just simplify, knowing that we're not dividing by 0 in any case, and we get the fact that r squared plus omega naught squared is equal to 0. It must be true. So what we said was, I want a solution of this form, where do keep in mind that r does not necessarily have to be real. In fact, we'll see later that r can be complex. Now, what this series of symbols means is that the variable r is an element of the complex numbers. And remember, complex numbers are all numbers of the form a plus bi, where I is the square root of -1. So it's not necessarily defining r as a real number. R can be imaginary. And remember, this is important for applying Euler's identity. So let's come back here. We're saying that if I want a solution of this form, it will be valid if this is also satisfied. Or rather, this needs to be satisfied for this to be true. So if we find a solution of this form that satisfies this requirement, where R rather satisfies this requirement, then we have found a solution to this differential equation of this form. So let's try it. Let's use the quadratic equation or the quadratic formula we have to solve this quadratic, because we have an unknown variable r here, and this is just a constant. So we can treat our a as 0, our b as 0, our a as 1, our b as 0, and our c as omega naught squared, and apply the quadratic formula. We have -0 plus or minus the square root of, now we don't have a b squared, we have a minus 4ac, but on the bottom we have a divided by 2, so we can just take out that 4, square root of 4 is 2, and cancel the 2's and save ourselves a step. This is going to imply that r, 1, and 2 are of the form plus or minus square root of negative ac, a being 1, therefore c is omega naught squared. Now you can see immediately why it was convenient to refactor k over m as omega naught squared. Because apart from this little negative term right here, which, by the way, is going to be the same thing as -1 times omega naught squared, which means we're going to have plus or minus negative square root of -1 being I, omega naught. It just makes it really nice. But at the end of the day, this is an equivalent value. This is just square root of k over m. Right, so now that we have this, let's go back and recall that our solution has to be of this form. So let's plug it in. We're going to say two things, that one of our x's is going to be equal to, and I'll omit writing x of t, you can keep it in mind, is going to be equal to some constant multiple of, because we don't necessarily know what constant multiple of, e to the rt, where r, let's choose the plus case, is equal to I omega naught t. And likewise, x2 is going to be the same thing except with a minus, so, and a different constant, e to the it, and my omega naught. Now, these are in different order, it doesn't really matter. It's addition and multiplication are commutative, so I just miswrote them in terms of order, but they're equivalent. Now, we can apply Euler's identity to both of these. Remember that the superposition, or the sum of solutions, is also going to be a solution to the differential equation. So if we expand these and then add them, that's going to be a solution. That summation is going to be a solution to this, right? It's going to be what we're calling the homogeneous solution. Homogeneous in this case means that this term is 0, but we'll get back to that later. So let's expand this first term. We have c1 times, this is going to expand to cosine of omega naught t plus, again, c1, I sine of, again, omega naught t. And then I'm going to continue adding, because we can add these solutions to get another solution, plus, and I'll continue down to this line, so I'll just put another plus there for continuity, c2 times cosine of, and notice cosine, as we recall, is an even function, right? If we take a look at cosine, kind of looks like, excuse my poor drawing, kind of looks like that, it's even. So cosine of some value is the same thing as cosine of negative that value. It's almost mirrored across the y-axis. So cosine of minus omega naught t is just the same thing as cosine of omega naught t. But sine is instead an odd function, right? It's, that may be a poor drawing, but the value of the sine of some value is going to be precisely negative the sine of the negative that value. So instead we'll write minus C2I sine of omega t, omega naught t. Now, it seems like we've just taken some nonsense solution, guess, and we worked around, we did some algebra, we got two complex exponentials, what do I do with that? And then we expanded them, and now we have four sinusoidal terms, two of which are imaginary. How is this helpful? Well, notice that R, even though it's a member of the complex numbers, even though it is a complex numbers, we can't forget that complex numbers are just constants themselves. So what we can do is we can group these terms, these cosines, and we can group these sines, and what we're going to get is the following. We're going to get C1 plus C2 cosine of omega naught t, and then we're going to get plus, just for neatness sake, C1, and I'll put these in parentheses, C1I minus C2I sine of omega t. Just to make this quicker, I'll copy it over. Right. Now, what do we notice about these? Well, a constant plus a constant, that's going to be another constant. I'm going to take this and call it C. And this is a constant, this is a constant, minus this is a constant, and this is a constant. All of this is itself also a constant. So we can call this C prime. So we see then that we can actually rewrite this equation as some constant, C, times, and again for brevity I'll just copy this over, times cosine of omega naught t, plus, really going fast here, some other constant, which is not necessarily the same, though it can be, it just doesn't have to be, times sine of omega naught t. Right? And this is a form that we like, because what is this? This is just a sum of cosine and sines. We can use this. In fact, it's useful. Why? Because recall, the derivative of sine is cosine, the derivative of cosine is negative sine, then we go negative cosine, then we go back to sine. It's a 4 cycle. And the reason it's useful to have both of them in the equation is because if we have a differential equation, which we do, when we take derivatives, if our solution was just sine or just cosine, we would end up with a mismatch. Because if we had a first derivative, we would have a sine term plus a cosine term, and there's no way they would cancel, at least not for all values of t. So we have to have both so we can manipulate these constants to allow our equation to be true so that the sine and cosine terms could cancel when plugged in. And then you can do as an exercise, find an initial value problem or make one up. And you'll see that you can find constants c and c prime such that this is true for whatever omega naught you end up with. And you see this is why it was useful to have that omega naught squared, because now we have a nice term here where this happens to be precisely the characteristic frequency of the system.